Imagine pressing your hand flat down onto the dead center of a concrete column. The column simply squeezes together under pure, uniform compression. But shift your hand to the edge and the physics change. By applying that force off-center, you are twisting the column while you push it. This introduces a bending effect right alongside the direct compression, creating unequal stress across the section and posing a much higher risk of failure. To analyze this, we mathematically translate that off-center load into two separate calculable components, a standard central axial load plus a bending moment. This graphic shows the principle of superposition. We calculate the flat, uniform direct stress, calculate the double triangle bending stress, and add them together. The resulting tilted trapezoidal shape reveals the exact maximum and minimum stresses, our primary tool for predicting failure. This is the combined stress equation for a single-axis eccentric load. It takes the base uniform stress, P over A, and multiplies it by a critical factor governed by the eccentricity, E, and the width, B. Notice the plus-minus sign. The minus is what we have to watch closely. Materials like concrete are strong in compression, but severely weak in tension. If that subtracted bending stress outweighs the base compressive stress, the column will crack. Looking at the middle diagram, increasing eccentricity tilts the stress profile steeper until the minimum stress reaches exactly 0. If the load moves even 1 millimeter past that point, the profile crosses the neutral axis, and that red zone indicates tensile stress has developed. Because concrete cannot reliably handle that tension, engineers must define a strict absolute geometric boundary for where loads can be applied. The line of action must stay inside this boundary to guarantee zero tensile stress anywhere in the section. For a solid rectangle, setting the minimum stress limit to 0 and solving for E reveals the maximum allowable eccentricity is B over 6. Doubling that gives a safe width of B over 3. The load must stay within the middle third of the base. A similar derivation applies to a solid circular section. The math caps the safe eccentricity at D over 8 from the center. This creates a central circular safe zone with a total diameter of D over 4, known as the middle quarter rule. When we look at hollow sections, the result is somewhat counterintuitive. Removing material from the center of the column alters the section modulus. Because the remaining mass is concentrated further from the neutral axis, the safe zone limits actually expand outward. This mathematically mapped safe zone is formally called the kernel or the core of the section. It provides a definitive boundary on a blueprint, allowing engineers to instantly verify if a loading configuration is safe. For a load off-center on both axes, this expanded superposition equation combines direct axial and both bending stresses. To avoid messy sign tracking, use the diagnostic tip. Maximum compressive stress occurs at the corner in the same mathematical quadrant as the load. For more complex, unsymmetrical shapes, we follow this strict 4-step workflow. You locate the center of gravity, calculate the moment of inertia strictly about those new centroidal axes, map your extreme coordinates, and finally apply superposition. Let's apply these rules to a gate-level prompt. Here is a 200 by 150 millimeter column with a 240 kilonewton load at a 10 millimeter eccentricity on the y-axis. Pause the video, calculate extreme stresses, and determine if tension occurs. Step 1. The direct stress is the force divided by area, giving us 8 megapascals of uniform compression. Step 2. Plugging the load, eccentricity, and section properties into the bending stress formula yields 2.4 megapascals. For step 3, we combine them. 8 plus 2.4 gives a maximum compressive stress of 10.4 megapascals. 8 minus 2.4 leaves a minimum stress of 5.6 megapascals on the opposite face, creating the tilted stress profile shown on the right. Finally, we perform the diagnostic check. The safe kernel limit for this axis is B over 6, which is 33.33 millimeters. Since our actual 10 millimeter eccentricity is well within that boundary, the math confirms our minimum stress stays positive and no tension develops. Here is the master matrix compiling all the critical kernel eccentricity limits we've derived for rectangular, circular, solid, and hollow sections. Memorizing these specific boundaries allow you to verify structural safety without deriving the equations from scratch. Take a screenshot of this frame. Having these limits committed to memory offers a massive time advantage when tackling competitive engineering exams.